Please use the chat to ask questions to everyone or directly to me, Shelley, or Mary. If you'd like to learn more about Our Lady St. Louis or get involved, we have a few ways to connect with us. Probably the best one would be on the Twitter feed, because all of us are on there looking at that feed probably more often than we are looking at our email or our Meetup. So, but any of those ways you can get in touch with us. And we also have a YouTube channel. You can go see all our past meetups that have been recorded. And so that's it for me. I'm going to stop sharing my screen after I introduce Laura Rose. She's a manager of demand at Mallinckrodt Pharmaceuticals. And I hear she has some potential opportunities to talk about there. She forecasts active pharmaceutical ingredients. She has experience with economic analysis and forecasting. After getting her MA in economics from UMSL, she uses R for time series, Shiny apps, and automating data analysis tasks. So without further ado, I'll stop sharing my screen and turn it over to Laura. Thank you so much for being here.
Sure thing. Okay. Well, that's not what I wanted to show. Okay, so I am going to be speaking on Arima models using R. This is an introductory presentation. So I'm assuming that you have no prior knowledge. I also assume that you're a bit familiar with base R, the tidyverse to some extent, and also you're comfortable with like basic algebra manipulation, that kind of a thing. So before I forget, I do want to mention the job opportunities that Janine mentioned. So I was actually speaking with a VP at my company and mentioned that I was giving this presentation tonight. He said, well, they're looking to hire some folks in pricing and some commercial operations and possibly forecasting. So competitive intelligence kinds of stuff. So if you are interested in that, I will say the company is probably more in the beginning stages of using data science. So be aware of that if depending on what you're looking for in an organization. But please feel free to reach out to me. I think Janine or Mary or Shelley have my email address. You can find me on LinkedIn too, and I will be happy to respond and help you out with anything you want to know. So if you're interested in pharma, please reach out. Okay, so let's kick it off. Arima models. They are one of the most common univariate, so that's using one time series forecasting methods. Arima stands for Auto-Regressive Integrated Moving Average. So how we're going to approach this tonight is we're going to look at each part of the Arima model in a fair amount of detail before we move on to implementing in R. So I'm going to try to intersperse some concepts with some code so it doesn't get too bogged down in the details. But I also want to make sure that we're spending enough time on the theoretical underpinnings of the model. Okay, normally one would put a bibliography at the end of a presentation. I like to put it at the beginning. These are two books that I used when preparing for this. Rob Hinman does some really great stuff with R and forecasting. Definitely check out his website. You can just Google Rob Hinman and time series and it'll take you to that. But he has a great book. It's on its third edition, Forecasting Principles and Practice, free online, or you can buy a copy. And then I also referenced Introductory Econometrics for Finance. From 2008, you can find a newer edition. It was actually, full disclosure, a college textbook of mine, which I had still saved, but which I found to be useful. So I guess I'm dating myself a little bit there. Anyways, this is a very good book as well. It is more based on e-views though. So if you want a good, more understanding of the theory behind Arima models, this is a good book. If you want a little bit simpler introduction, but a lot of good code and functions in R, this is a good book. And there are also a lot of great resources online that you can check out if you want to learn more about the theory behind these concepts. Okay, so we're going to start out with a very important concept for time series modeling and Arima specifically. That is stationarity. So a time series is said to be strictly stationary if the distribution of the observations does not change across time. However, many time series are not strictly stationary. We don't always need to have strict stationarity to model a time series. Many times you'll see reference to weak stationarity in analysis. So what are the assumptions of weak stationarity? Well, that's the expectation of y sub t. So we're dealing with a time scripted variable is mu, constant mean, a constant variance, and then we have a constant autocovariance. So the variance across observations. The t prime, if you're not super comfortable with subscripts, basically means a t which is not the original t. And there are different notation, there are different notations depending on the book you might look at or the paper, so just be aware of that. And of course, when t equals t prime, the autocovariance is the variance. Okay, so the autocovariance, as you might have guessed by looking at that equation, it's not particularly useful because it is scale dependent. That means you can have really big units if you have a big unit time series, and really small units if you have a small unit time series. So we often normalize the autocovariance by dividing it by the variance. And this is the autocorrelation, which you will see come up throughout this presentation. And the nice thing about the autocorrelation is it is bounded between plus and minus 1. So now let's talk about a special kind of case of a stationary process, and that is a white noise process. So the assumption of this is the expectation of y sub t is 0, as opposed to just mu, some constant. Of course, we have the sigma squared constant variance. And then we have for the autocovariance, right? Some point t prime, which is different than t, sigma squared if t equals t prime, but 0 otherwise. So we have 0 autocovariance unless we have t equals to t prime. Now I want to mention this because depending on which book or paper or Wikipedia article even or Stack Overflow answer which you read, some definitions of a white noise process do indicate a non-zero mean is permissible. It's not really a big deal if you think about it because you can just subtract out that mean value. Okay, so on the other side of the coin, let's talk about random walk. So random walk model is often used to denote a non-stationary time series. These kinds of models or series are very commonly used in finance, which is not our focus for today. So don't worry if you don't like finance, but just a note there if that is something you're interested in. So random walk model is basically y sub t equals y sub t minus 1 plus that white noise error term, or you can have a constant, which is called a random walk with drift. So C is the mean of the changes between the sequential observations. So you think about it, if C is greater than 0, the average change will tend towards an increase in Y over time. And of course, vice versa, if you have a negative C. So random walk series often have long periods of increases or decreases accompanied by sudden changes in direction. So again, the key word here is random. Okay, so I've introduced the concept of stationarity, talked about we want stationary series are ideal. So what do we do if our data is non-stationary? And when I say non-stationary, I would say it violates any of the weak stationarity conditions. So a little caveat here, data with trend or seasonality is not stationary. However, data that has cyclic behavior, for example, business or other cycles, which are not a fixed length, can be stationary. It does get a little tricky sometimes in practice, saying is something seasonal? Is this cyclic behavior? Is this like random walk? I'm just seeing a sudden spike and then it goes down. So when in doubt, you can do some tests, which we will discuss here, but I did want to note that. So differencing the series is a common way to deal with non-stationarity resulting from autocorrelation. Okay, so the difference of a value with the previous value is called first order differencing. That's often denoted as y prime sub t, sometimes without the t. And that is basically y sub t equal or minus y sub t minus 1. And note for a random walk model, if you difference it, you have basically a white noise process. So you have certainly made that stationary. Don't know why, just side note, don't know why the points jump when I do that, but little fun feature of sharing again. That's the package I use to create the slide deck. Okay, so sometimes taking a first difference is not enough to make the series stationary. So we take the difference of the differences. So what does that mean? So often this is denoted as y double, in the case of second differencing, right? Y double prime sub t. So we have y prime sub t minus y prime sub t minus 1. So substituting in, you get sort of, well, it's not, it's if this was x and this was squared, we would think this is a polynomial almost. And I'm kind of foreshadowing some stuff I'm going to get to later. But we have y sub t minus 2, y sub t minus 1 plus y sub t minus 2. And I'll offer a note of, I guess, caution or warning. If you're doing more than two differences, you should probably check yourself. Okay, so we might not just need to take first differences, right? We might notice a seasonal pattern. So we could take a seasonal first difference, right? Where yt minus y sub t minus m equals y prime sub t. Ideally, I haven't seen a different notation for that because that could be a little confusing. So it's always good to know what you're talking about if you're reading a book. But anyways, just keep in mind that M is the seasonal period. That might be 4 if it's quarters, 12 if it's months, 7 if it's week. So what happens if your data looks like it might require both first differencing and seasonal differencing? Well, then take the seasonal difference first. Sometimes this will be enough to make the series stationary. You might think you would need both, but you find out you don't. However, if you take a first difference first, you're not going to get rid of that seasonal. I'm sorry, typo there. I'll have to correct that before that seasonality. I'll correct that before and resubmit that to my GitHub repository. Okay, so you always want to use as few differences as possible. If you difference too much, if you kind of like, well, I want to make sure I can, not have any non-stationarity, you can induce patterns in the series that are not actually there. And then I'm going to make a little note here, and we'll come back to this. But if the variance appears not constant across time, remember that is one of the assumptions for weak stationarity, you can use a logarithmic transformation to stabilize, or another transformation depending on the data. And we will circle back to that in a bit. So testing for non-stationarity. So there are both formal and non-formal ways to examine the time series. And I recommend that you employ both. Always a good idea to start by plotting the time series. And this is assuming that you're not having to forecast like a bunch of time series at once. So line plot is generally good for time series. And the good news about just taking a look at your data is that often non-stationarity and non-constant variance are visible to the human eye. So if you look at your data, you suspect non-stationarity, then you want to plot the autocorrelation function and then check for those observations that are outside of the 95% confidence interval around 0. So we especially want to look at how quickly these autocorrelations drop to 0. And then to formally test for stationarity, we conduct a unit root test. What the test we'll use for the unit root is KPSS. There are also the augmented Dickey-Fuller and Phillips-Perron tests. Certain books recommend those. So basically you have several tests to choose from, and we're just going to stick with one of them for the purposes of this presentation. So unit root, what does that mean? Well, going back to the idea of the polynomials I alluded to, this implies that the data is essentially a function of its lag or lags, where the coefficient equals 1 plus some noise. There are variations on this. We're going to skip those for the sake of simplicity. I want to make sure I keep this focused on Arima and not on other cases where a unit root would be applicable. So in more formal terms, you might see that the root of the characteristic equation equals 1. We'll touch on that a little bit further on. Okay, so I want to take a little bit of a break from the theory. An example of checking for stationarity. It's pretty simple. So what I'm doing here, I'm going to walk you through this code. This is just some sales data. Actually, I think the statisticians Box and Jenkins, who you may have heard, like the Box-Cox transformation, they did a fair amount, Box especially around the middle of the 20th century. So this was some sales data that is part of the standard R data and was referenced in one of their texts, I believe. So what I'm doing here is I'm creating a date sequence. I don't really care where it starts, but it's monthly data. And then, we have 150 observations. So I'm going out by month. What I'm doing here is I'm calling tsibble, which is a time series tibble object. I'm going to create one of those. So the month is going to be converted to the year month type for date sequence. And then my time series data is that sales data. And then I'm saying for a tsibble, you need to specify the index. And that is going to be, of course, my month variable. So the index is the time variable. And then I call my handy autoplot function here, which knows to plot it as a line. So I can see I start out down here around 200, kind of some movement, shoots up here, and then kind of hanging out around 260 or so. So this series, when I look at this does not look stationary. So as I could probably guess that it's not a stationary time series by looking at it, right? Let's go back one. Non-constant mean across time. Variance actually doesn't look too bad, but definitely a non-constant mean. And looks like there is definitely some autocorrelation. There's in the series, which is not bad, but it's just something to be aware of. Okay, so checking the autocorrelation function. There's a handy function in the FEAS package called ACF, and then we'll pass that using our pipe to autoplot. So what are we looking at here? So this is 0. These are the lags of the time series correlated with the present lag, right? The present. So we see that as expected, there's less correlation in farther out lags as we go back. Lag 1 is almost at 1. So I'm thinking, yeah, unit root here, right? It's practically there. The important thing is to consider that this is our 95% confidence interval around 0. And all of these 20 lags, I believe, 24 possibly, are well outside of that. So this tells me that I'm going down the right path and assuming non-stationarity. So now let's look at the formal test for a unit root. So that's the KPSS test that I mentioned earlier. So I'm doing a lot of binding columns here. You could probably, if you were doing this yourself, you probably wouldn't need to call this, or you could make it a function to make it a little bit less repetitious. But I wanted to put all of these various calls into a nice little chart down here, table down here for you guys to see. So what I'm doing is I'm calling that sales tsibble object. And then the features function allows me to pass the variable, right? And then which is sales. And then I'm calling unit root KPSS. So this is actually a function, but I don't have it specified as a function in here. So this will give me, this is the first portion, and this will give me the null hypothesis is no unit root, right? So I have this very low p-value, so I would reject that null. So we don't need to just stop there. We can make it even easier on ourselves. And what I'm doing now in these last columns is I am calling another handy built-in function, unit root underscore ns diffs. And this is basically saying, okay, how many seasonal differences do I need on the data? Remember how I said that we want to look at seasonal differences first. Now, I probably don't need to do this because I can look at the data and I can say it's not really seasonal, but for the purposes of illustration, I wanted to do this. So I call that, and it tells me 0. Now I'm continuing this pipe. I'm binding this column again, and I'm calling n diffs. So this is just the first the regular differences, not the seasonal differences, which in this case would be a period of 12. So I wanted, if you look at my note that I put here, I'm not testing seasonally different data since there's no evidence of seasonality. So normally we'll see a different example of this later on. You would, if you suspected seasonality, and especially if you got an NS diffs equals 1, you would want to have that be the variable that you look at. And then finally, this is just some nice little formatting so it looks prettier on the slide. So what I'm seeing here is I need to difference the data to make it stationary, but I do not need to take a seasonal difference. Okay, backshift notation. I debated whether to include this because it's probably not strictly necessary for an introductory presentation, but it can help when you're looking at more complicated models, and you will see it if you really want to learn more about Arima models and kind of dive into some of the theory. So hopefully this will be helpful to you. It's a shorthand to describe lags of variables to manipulate it. So B is backshift. You might also see L for lag. So basically how we denote it is B times y sub t equals y sub t minus 1. So by extension, B times B y sub t equals, of course, B squared y sub t, and that is equal to y sub t minus 2. So you can imagine as you're going back how this plays out. So same quarter last year would be B to the 4th y sub t, which would equal y sub t minus 4. So we can also use the backshift operator to describe differencing. So going back to our difference definition, y prime sub t, yt minus y sub t minus 1, which equals y sub t, and then we substitute, of course, minus b y sub t. So 1 minus b, we can factor that out. We can factor out y sub t, and we get 1 minus b. So we can treat expressions in B like polynomials and solve for roots. That's the unit root concept. We'll say when you bring in the Arima coefficients, that will allow, if you solve for those, I would not recommend you necessarily do that because you can call functions in R that will allow you to do that. That will allow you to understand, is this a stationary model? So here's a little bit more complicated example. Y sub t double prime. You probably remember seeing this from a few minutes ago. So I'm substituting all these back shifts in, and then we can factor this out as a polynomial, right? We have b here. So 1 minus b squared y sub t. And remember that, so notice when we have a difference data, right? We have 1 minus b and then squared for 2 differences. So just keep that in mind because we will see it on later on. Okay, so we've gotten some notation down. Let's dive into the first portion of the Arima model, and that is auto-regressive models. AR models are kind of, can be standalone models. You can also think of it as part of the larger Arima framework. So what we are doing essentially with the AR model is we are forecasting a time series using a linear combination of prior values of the series. If you think about regression, we're basically regressing y sub t on itself, lags of itself. So an autoregressive model of order P, which is, we would say, an ARP model, it's written as follows. Keep in mind that epsilon sub t is a white noise process. So we have y sub t equals c, phi sub 1, y sub t minus 1, phi sub 2, y sub t minus 2, all the way back to phi sub p, y sub t minus p, and then our epsilon term. Okay, so AR1 models and how they relate to previous models. I'm going to mostly stick with AR1 just because it's a little bit conceptually easier. You can sort of extend it to more complicated models. But phi sub 1 is 0, c equals 0, right? It's white noise. Phi sub 1 equals 1, that coefficient is 1 and c equals 0. You've got the random walk. Of course, when c does not equal 0, random walk with drift. And then when phi sub 1 is negative, y sub t tends to fluctuate around its mean. Okay, so let's think about the stationary data, right? So we're going to estimate these coefficients as part of the process. So what kind of constraints do we need to have on these coefficients to basically have a stationary model? Well, for an AR1 model, it's very simple. You just had the phi sub 1 term, and it needs to be between -1 and 1. For AR2, that's then the phi sub 2 term has to be between plus and minus 1. And then there's some other conditions that they both of the coefficients need to add up to less than 1. The difference is also less than 1. Keep in mind that if you have an AR2 model, I don't think I stated this explicitly, so I want to make sure it's clear. That doesn't mean you just have phi sub 2, y sub t minus 2, right? You're going to have all the previous, the more recent observations there as well with their given coefficient. So the good news for you is when you're estimating your Arima model or AR model, these restrictions are handled. So you're not going to come up with a non-stationary combination of coefficients. Also restriction for higher orders of P. It gets pretty complicated after AR2. So don't worry about it, but just be aware of, especially for AR1 when you're looking at models. Okay, so let's make this a little more concrete. I am simulating some data here. I actually this is a base R function, arima.sim. I'm giving a list here. So this list is of orders. And that is basically, this is the AR term, this is the I term, and then this is the MA term. So I'm just saying I want to do AR1. I want that term to be equal to 0.7, right? So stationary. And then I'm just going to do 300 observations. Then I convert this to a tsibble, makes it easy to plot. So you can see I've got, a stationary looking series. We have kind of an outlier here, but overall nothing that is extremely concerning. And the point is, you're probably wondering, okay, why are you showing this to me? The point is that you're not going to guess that that's an AR1 process unless you knew it. So let's look at a few more time series. Okay, so I debated whether to put this in under the auto-regressive section. As you can see, my little asterisk there, but I wanted to contrast a stationary series, which was the previous one, with a non-stationary one. So note my little footnote here. This is technically not an AR1 model, but rather an Arima 1-1 model. So by putting this difference here, the integration I as 1, I'm basically saying, hey, to make this stationary, I need to difference this data. And notice I still have the same AR equals 0.7. So plotting this, right, you look at this, it's pretty obvious it's not stationary. You have definitely a non-constant mean, non-constant, maybe a little bit of non-constant variance, probably not that as much. But contrast that with this. So let's take a look at an AR2 process. Simple to simulate. I have just basically specified 2. And now I specify a vector of terms that would basically be my coefficients for each of the 2 terms. Okay, so I have this nice stationary looking time series. And the moral of the story is it's kind of hard to tell the difference between an AR2 process and an AR1 process by looking at the data. I'm going to do the same thing I did before for an AR2, technically an Arima 2-1 process, chosen the coefficients accordingly. And you can see that you have a very non-stationary series, right? So because I have this 1 here, it's basically, hey, it's not stationary. Okay, let's move on to the moving average portion. Okay, so y sub t is regressed on previous forecast errors. So what this basically looks like by definition, right? This is stationary because we have it's a combination of essentially a white noise process. So we have C, we have epsilon sub t, theta 1, epsilon sub t minus 1, going all the way back to theta q, epsilon sub t minus q. So we call this an MAQ model, or a moving average model of order Q. We don't observe epsilon sub t, right? We think about our forecast errors as being a proxy for them. These models aren't a regression in the sense that we would normally think about. And remember that epsilon sub t is a white noise process, mean 0 and constant variance. So depending on that value of C, that's going to give us different results. So here's an example of an MA1 process. You can see I'm following the same framework I was before, except for this time I have a 1 in the last vector of the order. I have MA equals 0.5 and simulating 300 observations. So we have a nice stationary series here. If you're anything like me, you probably would not be able to tell the difference between an MA1 and an AR1 by looking at it. Example of an MA2 process. So same process here. I'm going to plot this. Again, it's very similar to MA1, maybe a little bit less close, but other than that, it's very hard, unless you're much more skilled at picking out differences than I am, to see the difference between an MA1 and an MA2. Okay, so we looked at AR versus MA models. So now this is something I'm going to touch on, and we're not going to get really deep into this. It's a little bit more complicated concept, and I sort of regret not doing an extra slide on it, but there's some good resources that you can read up about in the books that I mentioned, as well as a Google search will turn up some good stuff, I'm sure. But this is basically how we relate AR to MA models and vice versa, as we'll see in the next slide. So we can express any stationary ARP model as an MA infinite model, order infinite, using backward substitution. So below is just a simple example for an AR1 model. So we have y sub t equals y sub 1, y sub t minus 1. So I'm going to substitute, just going back, and I keep substituting. I collect my terms. So you can see what's going on here, right? We have phi 1 squared e sub t minus 2, phi 1 e sub t minus 1 plus e sub t. And then as I go back and back, I'm going to get higher and higher order exponents for phi sub 1. And it'll eventually I guess well, you can see in this point, as when the absolute value of phi sub 1 is less than 1, right? As k approaches infinity, that will approach 0. So that's kind of what we talked about in MA infinite model, right? You're expressing essentially what started out as an AR1 as a series of past errors. So you can assume that this in the limit, this term goes away and we're left with etc. So what about MA relating MA to AR models? So an MAQ process can be inverted to an AR infinite process if we impose constraints on the parameters. So as I mentioned before, an MA model is by nature, it is a stationary process because of being a combination of those white noise error terms. However, the constraints that we impose on the parameters to be able to invert are somewhat similar to what we saw for an ARP process. So the current forecast error is a function of infinite past and current observations of the time series, as seen for an MA1 model. So this is basically the error term here, and we're going from I up to infinity. This is MA1, so we just have theta sub 1. And then we're raising that to the ith power. We're going back in time. So when theta sub 1, the absolute value, and that's less than 1, right? The impact of the observations on the current error, E sub t, epsilon sub t, declines as we go back in time. So I think intuitively that probably makes sense to you, right? You wouldn't expect that a way far back error is going to have more weight than the error from the previous time period. So if theta sub 1 is great, the absolute value is greater than 1, or if it is equal to 1, the distant past observations would not make sense. So that is the constraint that we are imposing. It's basically the same constraint as relating AR to MA models. Okay, so similar to an AR2 process, an MA2 process, and we're not going to go higher than that, it gets too complicated, is invertible when theta sub 2, absolute value is less than 1. Sum of the theta 1, theta 2 terms is greater than -1. The difference is less than 1. And you could prove that, but it's outside the scope of this presentation. And the nice thing is, Fable package will handle these constraints. Okay, so let's put it all together. So far, we've discussed AR models, MA models, kind of a whirlwind tour here, and then differencing time series to ensure stationarity. So that I stands for integration. So we have referred to the Arima PDQ model, as you saw in that simulated data, where you have that vector of three of length 3. And P, of course, is the AR part. D is the degree of differencing, and Q is the order of the MA part. So imagine we have a potentially difference time series. Let's maybe think of order 1. It would basically be something like this. So we have y prime sub t, then we have that constant, may or may not be 0. And then we have phi 1, and then we have all the way back to phi sub p, and then the same thing for theta 1, going back to theta sub q for our epsilons. An alternate way to express this, and this can be quite helpful for when you are looking at higher order models beyond just 1 or 2, is that backshift notation. So remember that 1 to the b the term that we looked at. So that's incorporated here. So we're putting all our y sub t terms on this side, just convention to have it on the left. And then we have think about how we would multiply this, right? The y sub t and b, we have this backshift going all the way back through phi sub p. And then on the right-hand side, we have the constant for convention. And then we have the same thing with that backshift notation. Then all these are multiplied by E sub t. So for example, this term here, theta sub 1b times E sub t would basically be E sub t minus 1. You could get rid of that if you were expanding it out. So that's this term right here. And keep in mind those invertibility conditions that we discussed for the AR and MA models apply to the respective parts of the Arima models. Okay, so special cases of Arima models that we previously have discussed. Probably a lot of these are intuitive to you guys, or you already thought of these. And that is a white noise Arima 000 without a constant. So I think one time I was modeling a series and I got back an Arima 000, maybe with a constant, but it was like, wow, okay. And it was something I wanted to forecast, which made it a little bit disappointing because you can't really find any patterns in a white noise series by definition. Then you have a random walk, and that is just 0, 1, 0 without a constant. And then you have a random walk with drift, 0, 1, 0 with a constant. An auto-regressive model is, of course, P00, as you would guess by that simulated data we looked at. And moving average would just be 0, 0, Q. Okay, so let's do some actual R coding here, or look at some R code. So what I'm going to do is I'm going to take that sales tsibble data that we looked at earlier, and I'm going to create a training data set. This is a good idea because you want to withhold data for testing. So what I'm doing here is I'm filtering the index. If you're familiar at all with fable or tsibble or feast, it's really easy to do. You can basically put the tilde, and then this is the last state that you want to include. And then I'm saving this model object as just fit. So the nice thing is I am calling Arima in this model function on the sales variable in the sales tsibble. So I'm going to let the algorithm sort that out. And now I have here report fit. You can just call, I think this is a broom function potentially. And I have my coefficients, so which are an AR1, MA1. So I see that what was chosen based on the algorithm was a 1, 1, 1 model. So I have order 1 for the AR part, order 1 for the MA part, and then I have 1 difference, which is probably not surprising to you all, looking at that very non-stationary time series and looking at the unit root analysis we did earlier. So I have my coefficients here, 0.88, so pretty high, and then negative 0.65 for MA, and my standard errors, sigma squared, and then I have 1.878. Not going to talk a lot about that, maybe a little bit later. Log likelihood, which we'll touch on later if we have time. And then we have these different information criterion, which we will go into a little more detail if we have time in the appendix. But notice the AICC. So this number by itself doesn't mean anything. So as you can see in the bullet point, the Hinman and Kandekar algorithm selects a model specification based on unit root tests, which we already looked at, maximum likelihood estimation for the parameters, and the minimization of the AICC, which is an information criterion. Interestingly, minimizing the AICC can be a good approximation for cross-validation. So it's a good way to select the model, and based on a stepwise search, which we will look at the details of that in just a second, this is the model that was selected. So the stepwise search does save time and can be useful for a lot of, when you're forecasting a lot of time series. If you want to do a more thorough search, use stepwise equals false. But it also means a limited amount of Arima models are considered. So I wanted to show you guys, take a short break, and show you this link here, which I found really interesting. So this is basically Dr. Hinman and his collaborators explaining how this works. So we have here the orders of P going up to 6, and then Q going this way up to 6. So kind of starting here at 0, 0. Keep in mind the difference of the data has already been determined at this point, the difference needed to make it stationary. So step 1, right? You are So it's going out. So looking at these different models. And then from here, we are going in one each direction. So saying basically which of these will we get a lower AICC. And in this case, it was this one. So then from here, we go out to ones we haven't looked at in one direction. Oh, this one. And then from here, we're searching ones we haven't looked at, right? We already looked at these, so we don't go back to those again. And none of these got a lower AICC. So then we stick with this order. There are also other arguments that you can use in the Arima, actually quite a few. You can restrict the values of the parameters, the coefficients. Don't recommend that you do that because you, frankly, I think a lot of us, myself included, don't know enough about what we're doing to make a good guess of that. So it's best to let, you want to let the algorithm have full potential to search. And even if you're specifying your own order, you definitely do not want to be restricting those parameters. Okay, so we've got a model, an Arima 111 model. Always a good idea to check out the residuals. Make sure there's no information contained that could be utilized in the model. So what I'm doing here, I'm doing the Young box test. That is a chi-square distribution test. I'm doing this for 12 lags. It's kind of a summation of lag function. And then I'm specifying 2 degrees of freedom. That's because I have those 2 parameters that were estimated. Notice the model did not choose a constant, which we'll get into a little bit more later on. Okay, so I'm calling this on the innovations residuals, the non-transformed residuals. Those are the ones we want to use. And I get the null of this is white noise. So if I don't reject, that means I'm probably good to go. And for this p-value, I'm not going to reject the null. Then I call the GG, this really handy little function, GGTS residuals, which looks at a line plot of the residual. So just to make sure there's no obvious patterns. Calls the autocorrelation function on the residuals. So remember when we looked at that autocorrelation function on that sales data, right? It was everything was outside that 95% confidence interval. Well, now we have everything going back 20 something lags. Everything's well within that 95% interval. And then we look at our residuals. Ideally, we like to see these normally distributed. They're not quite normal, but they're pretty good. This could just be a random, variation. It's not going to be perfectly normal. And even if that's the case, that would probably just basically, we wouldn't have realistic prediction intervals, but it wouldn't necessarily mean a bad model. Okay, so we've got a model in this case that we are comfortable enough with. The residuals look decent. It's been selected via minimization of the AICC, maximum likelihood estimation, and all that good stuff. So it's really, really, really simple to forecast within a Arima model and basically all models in the fable package. So you can use English language for the H argument, possibly other languages too, I'm not sure. Or you can just say the number of periods that you want to forecast. So those 80 and 95% prediction intervals are included automatically. You can specify level equals null if you don't want to show these on the plot. If you want to plot both the historical series and the forecast, because you want to not just see the forecast, you want to see it in comparison to the time series data, you'll need to specify the data as the first argument of the auto plot call. And we'll see an example of that. So we've got our fit object, forecasting 1 year ahead. It's going to be 12 months in this case. And I don't need to see the 80 percentile for the prediction intervals. So I'm just going to call sales sib. The nice thing is this is the whole data set. So we can see, yeah, so here we go. So here's our whole data set. And Arima 111 was basically mostly a straight line. And then we have this 95% confidence interval, which is increasing as we go forward. which makes sense because we are dealing with non-stationary data. So it looks like for the first few periods, we're doing pretty well. And then something happens here that we're not sure about. But all in all, we're still within that 95% interval and probably in the 80th percentile too. And the cool thing is about calling this is that it will automatically, you don't have to specify like filter this at all. It will line it up by index. So all the hard work is done for you. Checking the accuracy of our model. So measuring prediction or forecast accuracy is key. Anybody can create a model, but the question is, how useful is it? Recall that we withheld the data to use for testing our forecast, or rather it would be more accurate to say we created a training data set to use in fitting the model. And this is the validation set approach. There are other cross-validation approaches for time series. They're a little more complicated than the approaches for cross-sectional data. Those cross-validation approaches are outside the scope of this presentation, however. So the validation set approach is what we'll proceed with. So how are we going to look at this? Well, we're going to create the forecast. I say this as an object here, and then I'm calling the accuracy function. And I'm bringing it, if I did not put anything in this function, it would just be on the training data. But because I'm passing the full data set to it, again, the tidyverse can match it up by index and calculate the accuracy for me. And then this is just formatting for convenience sake. So got my RMSE of 3.65. I would say that RMSE and MACE, there's a lot of different metrics here. These are just point forecast accuracy measures, not to even mention distributional. I don't even use this one. MAPE can be good as long as you don't have any zeros in the data. Mean percent error, mean absolute error. Root mean squared error is often good. So 3.65, the MACE is 0.36. MACE is a metric. It's basically a scaled error. And the simplest way to say it is that it measures how well forecast performs relative to a naive forecast. So if it's less than 1, generally it means that it performs better than a naive forecast. Although I will say I have seen naive models that have MACE, well, they are greater than 1. So I haven't done a lot of digging into that, but it's more of a directional thing versus an absolute number. So RMSE of 3.65, considering we're dealing with units of 200 something, is not too bad. But of course, what is too bad would depend on the problem in question. Okay, so you've seen how to basically use the best fit algorithm essentially to fit an Arima model. But what if you want to specify the model yourself? You think you want to learn how to pick out those P's and Q's and the D's. So again, dating myself, back in my day, we didn't have Fable to select an Arima model for us. So we had to figure it out ourselves. So I remember sitting in time series forecasting classes, and the professor was talking about how to look at certain plots, which I will show you how to do. So if you are maybe a little bit of a masochist and you like to do the hard work yourself, or you think you can beat the algorithm, go for it. So we often rely on the ACF, which you've seen, the autocorrelation function, and the PACF plots as a starting point. So the PACF stands for partial autocorrelation function. So it's an autocorrelation function which controls for the effect of y t minus p, that furthermost significant lag, right, on y sub t, removing the effects of lags 1 through p minus 1 on y sub t. So essentially, a lot of times sometimes in the autocorrelation function, the effect of y sub t minus p might be mediated through other lags, as well as having a direct effect. So I almost, in econometrics parlance, I almost think about it as like holding all other included variables constant, if you've taken any econometrics or similar classes. So this is, keep in mind, P is the last lag. So this is the last significant lag in an ARP model. So we'll look at the last significant partial autocorrelation to give us an idea of the order of P, because everything beyond that would statistically be not different from 0. So if the data follows an Arima PD0 model, then for the difference data of degree D, often 1, the ACF will decay in an exponential or sinusoidal manner. The last significant spike and the PACF is at lag P with nothing after. Personal experience here. What is an exponential or sinusoidal manner versus significant spike? It's sometimes it's a little bit iffy, and that is the advantage of relying on the AICC to choose your model versus trying to guess it based on looking at these plots. Conversely, if the data follows an Arima 0DQ model, then for the difference data, the last significant spike on the ACF is at lag Q with nothing after. The PACF decays in an exponential or sinusoidal way. Basically the reverse of the first one we mentioned. Well, you probably noticed, well, what if both? Well, this is the bad news about when you have non-zero P and non-zero Q. So not always informative, especially in cases where both P and Q were not zero. Well, as you saw from our previous example, we had a case, and it's not uncommon to have a case where both P and Q are not zero. So that's where using the PACF and ACF gets tricky. Okay, so let's take a look at the PACF and ACF in R. So I'm going to go back to the sales data. We'll look at some other data too going further, but I want to just kind of take you through the process here. So look at the training data. I already know it needs to be differenced once, so I'm going to call it on the difference of sales. This is the first difference, and plot type equals partial. This is a really handy little function. You can specify different, it gives you the plot of the data, gives you the ACF, and then another plot of your choosing. So for this purpose, I'm choosing the partial plot. Well, I look at this and I say, okay, neither the PACF or the ACF seem to decay exponentially. So if I really wanted to go with the rules I just stated earlier, one of them should be decaying exponentially. Maybe this one, I mean, I don't know, it's a pretty big drop off from here to here. So that makes it a little more complicated. If I just wanted to start looking at significant lags, I could say, okay, well, 4, 2 are above, and then we already know it needs to be 1. This might be too complex. Be wary of going up really high in the order of P or Q. Ask yourself, do I need to do that? I would say probably better in this case to try out a 210 and a 014 and avoid getting this complex.
Hey, Laura, do you mind if I jump in for just a second? I think it's probably about time for us to take a little bit of a break.
Yeah, that's right. Absolutely.
Thank you so much. So why don't we say, okay, 5 minutes, and we'll start up at like 7:13-ish, 7:13, 7:15, you know, something like that. And for now,
it can go quickly. Learning curve is steep. Yes. I also use a lot of LaTeX for other things. I become way too good at doing equations in LaTeX. It's kind of a non-particularly useful skill to have, I guess, except for creating slides with a lot of equations on them. So, oh well. We ready to start back up? Okay.
That's great.
Let's keep on moving. Okay, so we're going to try out these models. And so what I'm doing here, training data. Remember, always don't peek, always use your training data. I'm going to specify an Arima 210, and that is this one. I'm going to do a 014, which going anything above 2 makes me nervous. And then I'm going to compare it, of course, to our Auto-Arima that we already saw, which is the 111. And then we'll call glance. I'm going to range in ascending order at the AICC. And then this is just selecting, there's some other columns in here, but we don't need them. And then formatting it. So surprise, surprise, we did not beat the algorithm, the Hinman-Kandahar algorithm. So I guess that's a little disappointing, but maybe it's a little bit comforting too that, hey, it's, it's a good algorithm. And me trying to guess the order of Arima models is not going to really do much other than waste my time. So just, you've already seen the auto-Arima residual. So I wanted to plot just one of these. I could have chosen, I guess this one's a little bit better, 210, but just to give you an idea of, even if you don't get the minimizing AICC model, which we assume that this is, we did not do a full search of the model space since we had stepwise equals true. But you could see my residual still look pretty good. The ACF, right? Nothing is outside of this 95% confidence interval. And these are a pretty nice normal-ish distribution. So if I went with this model, I wouldn't necessarily know that it could be better. And I might actually get decent results from this model. So I'm going to summarize in this slide the procedures for automating or for modeling an Arima process. You can do the automatic way. Transform the data if necessary to obtain constant variance. You need to do that yourself. You can't, and we'll look at that in a bit. You cannot have the Arima procedure do that. The Arima procedure will handle all the differencing, unit root stuff that we're looking at for stationarity, order selection. You'll check the residuals from the model to ensure they are white noise. A good idea to do that unless you have like a bazillion time series and you can't do that. And then you'll produce the forecast from automatically selected model. On the other hand, if you are a little more masochistic in regards to your Arima modeling process, you'll still follow the transform the data to obtain the constant variance. You'll review that data for stationarity via the process we observed earlier. You'll review those ACF and PACF plots of that stationary data and make some initial model guesses. You'll compare several reasonable candidate models. I would suggest concluding the automatically selected model since it's a good idea to know how close you are or not to the automatically selected model, and then choose the one which minimizes the AICC, or you might choose the BIC or just the AIC. Check the residuals from your model to ensure they are white noise, and then produce the forecast. So I alluded to this a little bit earlier about the constant and how we did not have a constant in that automatically selected Arima model. So there are some things that we should know about the constant as well as the degree of differencing in a model. So we can control whether or not a constant is included by the use of 0 preceding the PDQ special. For example, you might say model my Arima my variable, tilde, and then you got the 0, and then your whole PDQ. That would exclude it, or if you wanted to enforce a constant, you would put a 1 here. So if you've used the LM procedure at all in base R, that this syntax here of using 0 or 1 is probably pretty familiar. So if you don't specify anything, which I recommend you don't, it will be included depending on whether it minimizes the AICC or not. For D equals 0 or D equals 1. For D greater than 1, no constant. The constant can also affect the longer term forecast. So if you have a constant equals 0, like in our automatically selected model, the forecast will go to 0 if D equals 0. And that probably makes sense intuitively when you think about it. Your data is stationary, you didn't need to difference it. If you did difference it one time, they would go to that non-zero constant. Now, if you differenced it twice, again, be cautious getting up above one difference, the forecast become a straight line. So maybe not believable. I guess it depends on your situation. If the constant is non-zero, if D equals 0, the forecast would go to the mean of the data, which makes sense. D equals 1, they would follow the straight line. D equals 2, Dr. Hinman has said he does not allow this in the Arima function. If it was allowed, the forecast would follow a quadratic trend. If your forecast, that should probably give you pause because quadratic trend can quickly kind of get out of control. The degree of D also matters to the long-term forecast. So the greater the value of D, the more quickly the prediction intervals will increase in size. I referenced that earlier when we're looking at the Arima 111 model. You could see that as we went out in time, it was almost like a funnel. The prediction intervals got wider. Let's see another illustration of this. Look at our sales data. This time, though, I'm going to do two differences, and I'm going to plot it. So if I was just going by, I don't know, visual inspection, I actually might do this. Just the reason being, if you remember from earlier, that the first difference data, there might have been a few trends, you know, I mean, not necessarily bad, but, you know, okay, is that stationary? Possibly, possibly not. And then I plot the ACF and the PACF. So I'm going to say I already have two differences here. I'm going to say, well, maybe we can say this is decaying exponentially. I don't know. It's always a little bit iffy to me exactly what that is. But then we definitely have a clear significant lag at the one lag. So I'm going to just, for the sake of this illustration, do an Arima 021. So I'm going to compare that to the first one we specified, and that was the PDQ 111, and then the 021 here. And then let's forecast these, and we can plot both of them. So notice that the line forecast, if you squint hard, you might just be able to see that. They're basically the same, but notice that our Arima 021, we get wider more quickly. So essentially what I've done is something kind of not particularly smart. If I was to go with 021, I'm getting essentially the same forecast, which is reasonable given recent trends, right? The data is up to here. But my prediction interval is way wider. So why would I want to do that to myself? Okay, so in the time we have left, and I want to be cognizant of everyone's time, the elephant in the room, seasonal models. So we haven't done a whole, we touched on the concept of seasonality in terms of differencing. We haven't done a lot with it though, and I want to make sure you have an idea of how to approach it because it's a little bit more complicated. So usually you can see if there's strong seasonality in the data. This would be due to spikes at lags in the PACF and ACF plots, also patterns in a simple line plot of data. So the sales data we looked at does not really have a seasonal pattern. So I wanted to bring in some tourism data from Australia. And it is the purpose. So this is a big tourism tsibble, but across different states, different purposes, but I'm just going to do it for the purpose of holiday, or I guess as Americans might call it, vacation. So what I'm doing here, H stands for holiday tourism. I am basically grouping this tsibble, time series tsibble, the same way I would do using those tidyverse verbs. I'm grouping it by purpose. I don't care about state for the purposes of this analysis. I'm going to summarize it. Trips equals trips. And then the nice thing about it being a tsibble is that the time aspect is preserved. I'm just going to filter out the purpose equals holiday. And then I'm going to set up a training data set. So the data goes through 2017 Q4. So I'm going to leave out the last year, and then we will use that to test our model. So here's the data. I just do the training data. So you could see definitely, right, we have some seasonal spikes here. And then these troughs as well. However, we do have some non-constant variance. Down here, a lot less variation. Up here, over here, there's definitely more. So let's do some series transformation. So I could do a log transformation, but I want to be a little more analytical than that. So what I'm going to do is I'm going to bring out that handy features function, call that on the trips variable. And then I'm going to call the Guerrero function. So this is basically the Guerrero procedure for a box-Cox transformation to stabilize variance. So that will calculate the ideal value. I'm going to pull that out. So I just have like basically a vector of length 1 of that. And then what I'm going to do is I'm going to stabilize. I'm going to look at see how that stabilizes the variance. So I'm calling box Cox for the variance transformation on the trips variable, and then I'm using that lambda value that I calculated earlier. Okay, so here is the transformed series based on this procedure. I mean, kind of stabilize the variance, but it's probably the best we can do. Data is still non-stationary because it has that seasonality. So we'll need to take a difference. But do notice, right, before this was around 12,000 to 8,000. It's a lot narrower range. So even though we still see the same pattern, the scale has changed on the y-axis. Okay, so differencing seasonal data. You remember I said that we have seasonal data, we want to try seasonal differencing first and then see if we also need a first difference. So we're going to follow that procedure here. So I'm doing kind of some messy bind calls and stringing them together via a pipe, just to create this nice little table here. What I'm doing is on the training data, I'm calling that on the stabilized variance data, I'm calling first the NS diffs. So I know that this will give me 1. So then what I'm saying, okay, I do need to difference it once. So now what I'm going to do is I'm going to call this on the seasonally difference data. So I've got a couple of things embedded here. I've got that the variance data, and then I have the difference of 4 because this is quarterly data. So I need to take a difference of 4, going back 4 periods. And then I'm going to call unit root n diffs. And then I'm just cleaning this up by selecting this column. Again, a little bit of formatting here. So what I see is that for this data, I need to seasonally difference as well as I need to take a first difference. So lots of differencing. Okay, so this is more of an illustration thing here. What I am doing here is I'm going to add some series and then plot them. So the trips transform series is just the variance stabilized. Then I'm going to add a seasonally difference for the trips transformed. And then I'm going to take the difference on the transform seasonally difference, the first difference. So I've added all this to my tsibble, and now I'm going to pivot it longer. And this will basically allow me to more easily plot. So the variable names are going to be these different variables I created up here. And then the values will be trips, and then just create it as a factor because there's only like 3 or 4 variables. And then we are going to have free Y scales so we can see what's going on, but it can be a little tricky because you need to make sure that you're looking at the scale so that you don't have any false ideas about what's going on. And then I'm just removing these. I won't need them further on. So here's the original data. Here's the transform data. Notice again, has changed. It's gone down to about 1,000 versus like 4,000. And then we have the seasonally difference data, right? Notice that the length of the data set, of course, would decrease. I think that makes sense to you, but I want to point it out because when you difference, you lose data. And then we lose even more data by taking the first difference of the seasonal data. So we did the statistical test in the previous slide. Visually, there does seem to be some benefit. This seems to have a little bit of perhaps non-stationarity, a little bit of trend perhaps here, and taking a first difference in addition to the seasonal difference. So it's nice to see that our visual inspection of what's going on confirms what we are seeing in the tests. Okay, so we've got our transformed difference data. Let's call that handy TS display function. I'm just going to I'm doing a lot of pipes here within this function. So calling first the seasonal difference on the transform data. And then I'm going to call just first difference on that. And then of course, the plot type equals partial, lag max equals 20. So this again, we have that same series we saw earlier. So this is kind of an interesting thing to look at here. So you notice we have a significant spike at lag 4, which was a previous year, and lag 4 for the PACF. So that definitely implies even when we're doing this differencing, we still have that seasonality. Now, we also have a significant spike for the ACF at lag 1, and then for the PACF at lags 1 and 2. So that might be the non-seasonal orders. Now you might be wondering, well, what about this one? It's just kind of, there's like nothing here, and then we have lag, what is that, 5? We're not, keep in mind that because we have that 5%, right, type 2 error, there might be some lags that would be insignificant, but they are still outside of that 95% confidence interval. So these ones are not. There's no reason to think this is a seasonal pattern. So we're going to say, hey, we're not going to really pay attention to this. So we could do, again, we're not seeing any of that sinusoidal decay, so to speak. So we're left, if we're going to specify a model ourselves, we're kind of left to guess a little bit and try out different orders. So for seasonal notation, we might say, okay, Arima 2, these ones cut off after 2, 2, 1, 1, okay, that's significant. And then maybe a 1, we know we have the significant lag here and there. Remember the D, which is 1 for our regular difference, and then our seasonal difference. So this little subscript here is a way of saying that this is quarterly data. If this was monthly data, we would say 12. And these are our seasonal orders. So we'll see how we specify that in the R fable package. Okay, so Arima 21111 equals, again, using that variance stabilized value, PDQ21, and then a capital PDQ111. So use the the note that I have here is use the transformed but not differenced variables, since differences are specified in the formula. So just a note to keep in mind. Keep track of what you specify where, so you don't double specify a difference. And then just calling the Auto-Arima. And then we'll do that again on the same variance stabilized data. So we're doing the same thing we were doing earlier. And again, I guess we're not having good luck tonight. So we have the AICC is lower for the Auto-Arima model. So if you're curious to see what is the order that Auto-Arima specified, well, what was specified was 0, 1, 1, 0, 1, 1, and then 4. So essentially, what this is telling me is those AR terms that I have up here are really not useful in creating this model. And generally, simpler is better. So this leads me to think, okay, AICC is lower, it's simpler, that's generally better. I'm going to go with this model. Again, residual review, we always want to take a look at this. Yeah, the residuals look pretty good. We have the normal distribution is there, nothing outside of that 95% confidence interval. And then we'll forecast 1 year. So it's a little bit difficult, as I discovered, to save and then back transform for auto plotting model objects when you've done a transformation. So what I'm not using the fitted object I used earlier. I'm just going to call this again on the automatic specification, and then forecast, and then we'll take a look. Okay, so how do we do? Not great. We did pretty good for the winter months, but this trough season here, which would normally be, I think, Q3 and Q4, that's the winter and spring months for Australia, it was quite a bit higher than what the model predicted. In fact, even going outside of that 95% range. So we predicted down here, and here's the model up here. So what can we say about that? Well, I'm not super surprised. This is what was predicted. If you look at this previous value, you look at the peaks and troughs going back. So we have a lot less variation right here. And also, fun little fact, notice that the back transformation was handled automatically for you. Even though we modeled on the transformed variable, we get the forecast back in the non-transformed variable. So again, what can we learn from this? Well, this is a case of where a model with external regressors, like a time series model, perhaps a co-integrated model, something else like that, a machine learning model might be helpful in predicting this uptick in travel. So something was probably going on in 2017 that made, even in the off season, more people go to Australia. So who knows? So let's look at the forecast accuracy. It's generally the same. Just, I'm going to add a little bit of something here. I'm going to estimate a seasonal naive model because it's always good to see, do we outperform a seasonal naive model? We have seasonal data, so that's why I'm using the seasonal naive. So hopefully this framework looks familiar to you. Well, the good news is, even though our MACE was not so great, it was still better than the seasonal naive model. So we have the RMSE is slightly better. Okay, in our last section, I want to talk about estimating models for multiple series. This is a very much of a business case type of situation. Usually you're not going to have the time and luxury to, tweak a model for like one time series. It's really easy to do this in Fable. You could have a tsibble with multiple series. The key structure, which we haven't really explored a lot, but definitely recommend you read up on that, will denote that will denote different series, and Fable can kind of figure out that we want a separate model for each series. Note, for this to work, you need the data to be in long format. So let's take a look at the full tourism data set. It's like 300 something series, 304, I say. So again, we're going to create that training data. I'm just going to do holiday, otherwise it gets really, it takes a long time to estimate. So I'm going to model Arima trips, and then I'm going to do the seasonal naive trips. You'll notice I'm not checking for non-constant variance. The fact that it would be nice, and I guess I could perhaps calculate Guerrero values for all of them, maybe join those back in, but it's not always feasible when you have like a bunch of series. So let's take a look. There's too many to fit on a slide, but let's take a look at the first 6. So this one is region of Canberra, state ACT. Okay, well, this is kind of a little discouraging. Seasonal naive does better, does better than the Arima. Another one, seasonal naive, does better than the Arima. Now this is one where we have the Arima doing better than the seasonal naive. And again, I'm only looking at the first 3 here. So we'd have to, I guess I could have calculated means and looked at overall what it was, or you could do that on your own. With the .rmd file if you wanted to play around with it. So that is the fact of the matter, is it's not always pretty, and sometimes you don't beat the seasonal naive model, and sometimes you do. Okay, so I think I'm going to finish up here, and then I think we'll have time to go through the appendix slides really quick. So the conclusion I want you to take away from, they're very commonly used. The models are useful when you believe the data are a function of previous values and or previous errors, forecast errors. You don't have access to or are unaware of other predictor variables. I feel in recent years, as machine learning methods have become very popular, and rightly so, Arima have kind of been, I say, gotten a bad rap, but it's kind of like, oh, why would you do that? Well, sometimes, we can't all have like the beautiful model, or it's like a racehorse. Sometimes you have a beautiful racehorse, other times you got the workhorse, and the workhorse can get stuff done. And that's kind of how I feel about Arima a lot of these days. The nice thing about Fable, Feast, and Tsibble is that you can produce many Arima models quickly with minimal code. Especially, you don't need to use per, for loops, etc., which you need to use in other contexts for many time series. Creating many time series models. So, and then I'll quickly go through the appendix slides. Parameter estimation. Maximum likelihood estimation is used for estimating parameter values. Basically what it is a search for the parameters that maximizes the likelihood, or loosely termed probability. They're not quite the same, but the data arose from process with such parameters. So in the Rima context, MLE is kind of literally squares in terms of like that loss function, minimizing the sum of squared residuals. So note that when we call report on a Mabel object, remember way back earlier tonight, we did that, you see an entry for log likelihood. So this is basically, as the name implies, the logarithm of the likelihood that the data arose from the model we estimated. So we want to maximize this value through AICC as information criterion that lets us know how well we're doing on that. And that's commonly used, but AICC kind of incorporates that, so we use that more as a measure of model accuracy. Okay, so you heard me talk about the AICC a lot. It's one of several information criterion that are used. There's also the Bayesian information criterion, which I don't think is actually Bayesian necessarily. But note that when you compare models using the AICC, the y sub t variable must be the same. We cannot use AICC to compare models between models with a different D or degree of differencing. And that is partially, when you think about it, you have in the AICC, I believe, you have the number of observations T is a factor in the calculation. So if you're using a different degree of differencing, you're going to have a different T. So you're not going to compare apples to apples. So the AICC not corrected is basically -2. The 2 I've been told is basically it's historical purposes times the log likelihood plus 2 times the number of parameters, and the parameters includes the sigma, estimated sigma. The AICC more heavily penalizes the number of parameters, especially as it relates to observations in the model. So that means since we want to minimize the AICC, consider the -2. If you have a negative number with a higher magnitude, that's better. And finally, prediction intervals. As I mentioned earlier, that with an increase of width the prediction intervals is related to the degree of differencing. It's kind of complex to get to the prediction interval calculation for Rima models, especially beyond the first period. So the nice thing is the first period, that y hat t plus 1, the capital T implies all the last observation. You just use that estimated the estimated sigma hat, standard deviation of the residuals, plus or minus 1.96. You know, the 95% I guess Z score. Consider that this is because the inputs we have for the model are known, but beyond t plus 1, we're having to use forecasted inputs for certain or all values. So for an Arima 0Q model, it's a little bit simpler. So basically our MA models, your sigma hat squares, so our at period H out in the future is basically that variance of the residuals, and then you have multiplied by for everything up to H minus 1, that parameter, the parameters that are squared. So it's kind of a wonky formula, but if you're some reason want to do it by hand, I guess now you know. And recall that you could, if you really wanted to hand calculate a stationary ARP model, prediction intervals, you can invert that as an MA infinite model. So you kind of back your way into it if you wanted to do that. Again, I don't recommend you try that at home. Why not take advantage of the capabilities of R and Fable and save yourself some trouble. So, okay, well, that is all that I have. And I guess we have time for some questions. I don't know what we want to do.
Thanks so much, Laura. Yeah, I think we have a few minutes left. We usually put 6 to 8 on our invitation. Some go longer, some go shorter. So if anyone has questions for Laura, that would be fantastic.
Hey, Laura, the slide where you talked about how you were doing 300